So let's move on. Let's go to the, let's look at the condition where we are not dealing with a line of perfect length, of half wave, or multiples of a half wave. And there's two reasons why we want to look at this critically. Well, actually, I guess it's really the same reason, but it's two problems that come up when dealing with, I don't want to say irregular line lengths, but let me say this right off the bat. Anytime you see an antenna system where a specific length of transmission line is specified, you've got a problem. That antenna is only going to work optimally on the one frequency for which that antenna transmission line is cut. Now, that's not my opinion. That's a fact of physics. That's just the way it is. If you have an antenna, I'll give an example. Louis Varney, G5RV. When Lou Varney developed the G5RV, he developed it as a 20-meter antenna. That's what it is. It's a 20-meter antenna. That's why the length of that line is what it is. If you if you use an impedance matching balun at the end of that line, that antenna will work. If you try using it with or without a balun on any other frequency, you can get away with matching it with a tuner. The impedance presented by that combination of antenna length and feed line is such that most tuners can tune it. But it is in no way a resonant antenna. It is in no way designed to operate at any frequencies other than 20 meters. It simply is tunable. Whereas if you eliminated that feed line, and that's what we're going to show you how that works. I'm not going to show you specifically with the G5RV, although maybe I will. Then at any other frequency, on other bands without that sectional line, you would be presented with impedances that most tuners could not handle. You know, over 3,000 ohms, forget about it. Under 30 ohms, under 20 ohms, well, under 20 ohms, forget it. Most tuners cannot handle that extreme of impedance to try to mismatch, to try to correct. But you put this section of line on there, and you know it brings 3,000 on one band down to 300. I mean, okay, you can deal with that, and you get wild, crazy reactances. It's reactive on all those frequencies. It's highly reactive, but it's within the tunability range of most tuners. But it was never designed to be. It is not a multi-band antenna. Okay, so let's talk about imperfect lines. Now, again, I'm going to go to my graph. I'm not going to draw a line. We're going to do a graph. And we've already discussed the quarter wave condition. So you know that at any multiple of a half wave, the impedance at the end of the line is what you see at the input of the line. If you have an SWR there, it's going to be the same SWR here. You're going to get that condition is going to be mimicked. In the case of the quarter wave, you have exactly the opposite. A short appears as an open. An open appears as a short. You get a complete inversion of the impedance. A capacitance will appear as an inductance. A short antenna will appear as a long antenna. It's weird, but anyway. So between a quarter wave and a half wave, you have everything else. So what are we concerned with here? If we have a quarter wave and the condition between a half wave and a quarter wave is basically the same as anything between a quarter wave and a half wave, or a half wave and a three-quarter wave, or a three-quarter wave and a full wave, and a full wave and, well, we're back to a quarter wave again, aren't we? So you have if we isolate the quarter wave condition and we isolate what is very nearly the half wave conditions, then everything else is this gray area in here. Okay? And these are these red areas, quarter lambda condition, which is really bad. We don't want to go there normally unless we have a deliberate reason for having a quarter wave section somewhere on our antenna system. So we don't want to deal with quarter wave sections. All bad. And then we have these half wave sections, or I should say it's lambda n over 2, because you can have any number of them. All even. All even. Or odd. It could be odd. This, however, is only odd. If you have an even number of quarter waves, what do you have? You have a half wave. Okay, so this is only odd. Okay. Given this gray area, that's a lot of possible coax lengths. I mean, if we allow this optimum and avoidable condition to be, I don't know, plus or minus a few degrees, then that's a lot of conditions that are not necessarily perfect. But they could be. They could be. So let's take a condition. I'm going to pick a number at random and put my brain into random mode here, and I want to be more than 270. 300. How's that sound? 300 degrees. I like 300. So 0, 90, 270, and 30 more. 300 degrees. Okay? So what's the condition at 300 if I have a reflected signal? Let's say I have a voltage reflection. I have a high impedance termination. I have predominantly a voltage coming back at 180 degrees. So 180 degrees plus 300 is 480. 360 from 480, just to get rid of a wavelength, what the hell. 360 from 480 is 120 degrees, isn't it? Yes. So starting at 120 degrees, which is roughly here, I guess. So we're starting here, it's a negative slope, and that's going to be reflected back. So I think it should be crossing there. Okay, so there's our reflected signal. That's what our reflected signal is going to look like, more or less. Actually, these should be, if I did this right, these will appear parallel here. All right, so there's our signal. So we're going to have a high voltage condition in most cases, well, depending on how much is being reflected back. But we're going to have a higher voltage condition. It's going to sum to a greater number. However, here's the thing. The standing wave ratio is going to be the same as it would be in the case if it were a half wave. The 180 degrees difference between the components of the reflected signal still holds true. But here's what's different. If I continue this waveform out, okay, so that you can see where it's zero and where it's not. If I take a piece of coax, say like a 6-foot piece of coax, and then I put my SWR bridge in line, and then I connect my coax going on out the station, and then I have my radio here, okay? If I add a 6-foot piece of coax and a bridge, I have changed this whole relationship. I have shifted this. I have shifted these waveforms in their relationship to one another. This line is no longer 300 degrees. It just became 320 or 380, depending on what frequency I'm on. Because of the way the bridge works, this will change your readings. You can, and this is where a lot of people get all fouled up, you can find a length of line where this reflected signal and the forward and reflected signal will combine in such a way that you will get a minimum reading. You will get a standing wave ratio that appears sufficient at a certain point. You know, you trim your coax and all of a sudden it looks good and you go with it. And then you take the meter out of line and all of a sudden the radio's telling you have a high SWR. You put your meter back in line, everybody's happy. Wait a minute, what's going on here? You change your jumper. You go from a 3-foot jumper to a 6-foot jumper. You're using a 3-foot jumper to do testing. And then you put your station all back together and you find out, oh, I need a 6-foot jumper to go from a coax switch over here to my metering rack over here. So you put a couple of more cables in and now you got everything all hooked up and everybody's happy and you flip the switches on and all your standing wave, all of your metering's different. That's not how it was when I was testing. What happened? I was almost at 1-to-1 on 14.200 before. Now it's like 3-to-1. What's going on? Meter position in your line. You can find conditions where the meter is happy. You can slotted line. I started this off talking about the slotted line in the microwave class. You can slide that meter up and down your line and find a spot where it's happy. Doesn't mean it's right. You can find a location where the ratio of current to voltage, because it's shifted by a non-zero value, a not 180 degree value, because it's shifted, you can find a location where the ratio of current to voltage, because remember, what did I say? You're not metering forward and reverse currents. You're metering a single composite standing wave. That's all that exists in the line. The ratio of current to voltage is what this meter is reading. And because they're shifted, you can probably find a place in this line where the ratio of forward to reflected is such that it appears you have a happy reading. Now here's the rub. If you know exactly what your power level into the line is, you will see the power level will be wacky. The power level reading will be completely wrong, but your forward to reflected ratios will tell you you've got a great standing wave ratio. But it says you have 200 watts or 20 watts when you know your radio's putting out 100. So that's the telltale. That's the telltale. You can find the ratio which is correct, but the absolute magnitude, the absolute level of voltage or level of current which is being utilized to actually tell you what your power is will be totally wrong. So anyway, so what I call the non-zero condition. That's my term. Or the non-integer condition, if you want to deal with half waves, it's the non-integer condition. You're not at a half wave point. What can you do about this? Well, two things. You can't cut every piece of cable to a half wavelength, and in fact you shouldn't, because what did I say before when we started this? Anytime you see a length of cable, a transmission line in an antenna system, which has to be a specific length, you got a problem. You got a problem. That is not an antenna system you want to run. I mean, well, maybe it is on a specific band. I mean, there's a reason for doing that if you need to do that. But you're talking a monoband antenna, an antenna for one frequency. And it can work out very well for you. Tuned feeders. I mean, look at phased arrays. I mean, how do you phase an array? You put delay lines in of a specific length. Okay. You need to be aware of this. There's nothing wrong with these non-integer lengths of cable. So how do you correct for this? Well, you correct for this by having your lines matched, and that's the next topic. Can you use a tuner? Yes. We'll get into that in a moment. One other thing about this, and this may not be doable for HF, it may only be doable for VHF and UHF. And one of the things we did was, of course, you know, we used a bird meter, and one of the things about a bird meter, everybody says bird watts. You gotta measure that in bird watts. Is a bird watt meter any better or any more accurate than a Heathkit? No, not really. But it may be better made, and that's the key. It is a very, very well made antenna. That 50 ohm section of line in a bird, that 50 ohm section of line is 50 ohms. It's not 49, it's not 51, it's 50, and it's silver plated. and it's low loss, and it's reliable, and it'll give you, you know, rugged, durable piece of test equipment. And it's calibrated, I think it's plus or minus 1% full scale, which is not a lot. I mean, that's not like super high accuracy. But it's repeatable. It's plus or minus 1% at 20 degrees and 110 degrees, and as across the specific frequency band, it's very flat. It's very accurate. I mean, you know, from I think what's maybe 100 to 250. From 100 to 250 megahertz, it's you know, it's flat within a few, you know, fractions of a dB. I mean, that's what a bird is. Is it more accurate? No. Is it reliable and repeatable? Yes. So that's what a bird is about. So you know, good stuff. But when you buy a bird, they tell you exactly what this length is. They tell you exactly what the length is, and they tell you the velocity factor of that length. And I don't remember what it is. I think it's 4.5 inches or 5 inches or something like that. And the velocity factor is damn near 90. I think it's 92. It might be it might be higher actually. It's and the reason why they tell you that is so that you can make up jumper cables that for VHF and UHF end up being exactly a multiple of a half wave when all is said and done. So when you open up my bird box, you will see jumper cables that are 12 inches long and 6 inches long and 8 inches long, and I got a variety of lengths in there. And they are specific lengths to give me a half wave at 2 meters, 220, 440, etc. And the reason being is that when I put my bird in the line, here's the antenna line that I'm testing, okay? Here's my test line. The impedance here, this Z, when I put that half wave section on there, is exactly the same as the Z there. It has to be. It's a half wave. It's important. Cutting your coax to a length that makes your meter happy does not fix your SWR. Finding a jumper cable and putting it on your test meter, picking a cable, picking a jumper that gives you a good reading, does not mean your antenna system is matched. It means your meter's happy. Okay. I want to talk about metering. It's kind of misunderstood how metering really works. And I want to draw one simple meter. This is a Bruin bridge, and it is the most common, I believe that's how you spell it, Bruin bridge. And this this design was probably most popularized by Collins Radio, and it's a good bridge, and it's what you'll see most often for certainly for HF. And there's variations of it for other frequencies, and there's strip for higher frequencies. They do pretty much the same thing as strip line techniques and what have you. But basically, it's a piece of coax, and of course there's a there's a connector. Usually they have a SO239 on each end, so you have a proper termination for your coax. This is a coaxial section. It's obviously 50 ohms, but it could be something else if you so desire. You could make one out of a 75 ohm cable. And one end of this section is grounded. Obviously, there would be a box, some sort of an enclosure, and that would be grounded as well. But it's important that only one end of this shielded line section be grounded, because you do not want any current flowing on this section. Any ground current that needs to be coupled from input to output must go through the box, not the shield. This is just an electrostatic shield. It does create a 50 ohm line, and it prevents voltages from coupling to the transformer. Now, the way this works, remember we said, getting back to key concepts here, there is not a forward and a reverse voltage in the line. There is only the standing wave. There is one composite current and voltage at any point in that line. But we can still meter forward and reflected waves in a sense, in that the relationship between the power in the line traveling technically in one direction and back in the other direction is related by 180 degrees. We said the reflected component, the major reflected component of the signal from the load back to the generator is always shifted 180 degrees. Well, it could be 180 degrees plus or minus line length, obviously. We know that. So what we're going to do is we're going to make a transformer by winding several turns of wire around this line. Now, most often you will see this in the form of a toroid with quite a few turns of wire. Okay, so you'll have quite a few turns of wire around the toroid, and then your transmission line will, of course, travel through this. So that's your primary and your secondary. I've seen it a number of ways schematically, but primary and secondary. Now, so this is your current. That's metering your current. It's isolated from voltage by the shield of the line. And off of the line here, we'll have some capacitors. And these are variable. And they obviously represent the voltage. So we bring these together and terminate them in a resistance fairly low, about 50 ohms. And I've seen them terminated in lower values as well, or higher values for that matter. Okay. And then finally, rectified. And one of these is going to be forward, and one is going to be reflected. This current winding develops a voltage at this point and at this point, and the relationship between these two windings on the AC waveform from any transformer. Okay, what is the relationship between A and B here? Doesn't matter what it is. 60 cycles, could be anything. What's the relationship, phase relationship between A and B? It has to be 180 degrees. So, and I like the version where you have a center tap here. It doesn't need to be center tap. I just happen to like the ones that are center tapped. I think they tune a little easier, but it doesn't really matter. It works both ways, even when it's floating. So we develop a voltage here that, for lack of a better description, we'll call it positive, or in phase with the current. And on the other side, make that very clear, on the other side we'll develop a voltage which is 180 degrees out of phase with the current. Over here we have a voltage. This is our voltage, this is our current, and we'll call this positive, just because. Just pick a reference. So in this condition, positive and positive, we're going to get a, in the case of the forward, the magnitudes of the forward wave are always in phase. They start out in phase with each other. The magnitudes of the reflected, they're always going to be 180 degrees out of phase. Either the voltage is going to be reflected out of phase, or the current is going to be reflected out of phase. But either way, whatever its magnitude, they're going to be separated by 180 degrees. So let's take the case where the forward signal is a matched condition, perfectly in phase. We have two voltages which come together, are rectified to operate a meter. Our meter is out here. Okay? And we can switch. We can switch between forward and reflected as you like. All right? So these sum up here, rectified, and gives you a forward reading. When we flip this to the reverse side, we now have the same, not a different, remember, there's only one signal in the line. The signal in the line is the exact same signal we had here, except now it appears here, 180 degrees out of phase. So this voltage and this voltage cancel to zero. And that's how you calibrate this. You terminate this in a perfect load, in a matched load, and you adjust your reflected power for zero. And then you take your matched load and you put it on the opposite end, put your transmitter on the load end, and go the other way and adjust this for zero. So now both forward and reflected are not calibrated, but they're balanced. You balance them out for zero. So the voltage and the current for a 50 ohm matched line condition cancel out to zero. So what happens when you get an unmatched condition? When you get an unmatched condition, again, you have the summation of all of these waves in the line, producing a single wave. Whether it's phase shifted or not, due to line length or reactance at the load, really doesn't matter. What you've got is a wave coming back, which is going to sum to a condition where either the voltage is going to rise and the current's going to drop, or the current's going to rise and the voltage is going to drop. Those are the two situations. There's no others. Either way, the relationship between current and voltage is just a ratio now. We're not dealing with any numbers, no magnitudes. It's just a ratio. The ratio that you adjusted these caps to zero out at no longer holds true. And the relationship between forward and reflected, the error between those two is exactly equivalent to the forward versus the reflected waveforms. So now if you flip to reverse and you get a reading because the ratio is out of balance. Load's not matched. It's not 50 ohms. The ratio of current to voltage, the standing wave, no longer has that. Remember I said initially we had 10 volts on the line at 50 ohms was 200 milliamps. So that's our ratio, right? 20 milliamps per volt. If the impedance goes up, the voltage rises. The impedance goes up, voltage rises, current drops. Vice versa. Impedance goes down, voltage drops, current rises. Either way, that ratio, that error in that ratio will be reflected here. Very simple, not complicated system at all. If you want to operate into a 70 ohm system, you can recalibrate these. You can readjust these for the new ratio to match the 70 ohm system. Now you put it on a 50 ohm load and it says, hey, you've got SWR, even though you may not. It doesn't really know. All it knows is, do I see a 20 mil to 1 volt ratio at 50 ohms? I'm in a 50 ohm, I'm adjusted for a 50 ohm system. Do I see that ratio, that balance? Am I balanced? If I'm not balanced, okay, you get it. So anyway, Bruin Bridge, very simple. It's a good thing to know. But now you know how they work. All they're doing is looking at the ratio of voltage to current and it's determining that at 180 degrees and 0 degrees. And if all the voltage and current is at 0 degrees and none of it is visible at 180, you have nothing reflected. That's how it differentiates between forward and reflected. Even though forward and reflected really don't exist. I want to talk about using velocity factor to troubleshoot. This is a simple thing. You have a piece of coax. It's buried. You got 250 feet of coax going underneath your front lawn out to a antenna tower or dipole or a phased array in your yard, in your backwoods or whatever. But you got this wires buried and your SWR sucks. And so you go out, you drop your antenna, you put a dummy load on there just to check it out. You come back in, check it, still no good. You got a problem in the wire, you don't know where it is. You don't want to dig up your whole backyard. You need to find out where the problem is. How do we do that? Without buying fancy equipment. You can go, well, you might be able to go find an antenna analyzer that'll help you out, but when it comes to small anomalies, I find they're not all that sensitive. But anyway, here's if you have an oscilloscope, here's a neat trick. We're going to build a simple time domain reflectometer. We're going to take our coax of some length, and we're going to find out how far from the feed point our problem is. And the way we're going to do that is I'm going to take a resistor. Usually, I usually start off with about 10 times the characteristic impedance of the cable. So you figure about 500 ohms. And I put that in series with my cable. 500 ohms. And I take my oscilloscope and I take my signal into my vertical input here, and I take a square wave. Okay. Now you can use a signal generator, or you could just use a switch. Just a simple switch. Just close the contact manually by hand. If you don't have a signal generator, you can't generate a pulse. And I'm going to put that into here. And I'm also going to trigger my scope with that same signal. So now when I look on my scope trace, I see the initial rise time, the leading edge of that trace. And at some point, there'll be an anomaly in that trace. It'll either go up or it'll go down by some small amount. If it's really, really, really a small amount, you can increase the value of that resistor or make it a little more sensitive. But it'll go up or down by a very, very small amount, and then you'll see the rest of the waveform, and it'll go back. So we're going to measure the time difference between T0 and T whatever's getting reflected there. And in this case, it's going to be 0.1 microseconds, or so 0.1 microseconds is what I measure between those 2 points. So where's my problem? We're going to use the speed of light. We're going to use velocity factor. So we know the speed of light, c, is 300 meters per second, 300 million, 3 times 10 to the 6th meters per second, or 983 million feet per second, if you want to use feet. And we know the velocity factor because we bought cheap cable. We bought, you know, the polyethylene stuff, is 0.66. So it's not going to get quite as far as we'd like. It's going to get 66% of that in 0.1 microseconds. Okay? So 300 million times 0.66 equals, times 0.1. Sorry, very important. Times 0.1 times 10 to the negative 6th microseconds, right? So we can get rid of, this is 10 to the minus 6, 10 to the 6, we just forget about that. So 300, right, times 0.66 times 0.1 is 27. Ah, 19.8. Actually, there's one little more thing you got to worry about here. Equals 19.8 meters. So, is it 19.8 meters to my problem? No. It's 19.8 meters to my problem and back. I got to account for the back, the coming back. So, round trip from t equals 0 out to some point, to some problem, and back is 19.8 total. So the actual distance to my problem is 9.9, yeah, 9.9 meters. Oh, not millimeters, meters. So it's 9.9 meters to this point. I don't know what's wrong, but if I take my tape measure and I run it out 9.9 meters and dig a hole, I'll bet I find where a gopher chewed through my coax. This works. You don't need any fancy equipment. You need a scope and you need to make a pulse. And that's all you need. Now, what I'm illustrating here, in addition to giving you a little trick to put in your toolbox, is reflections have to travel back. Okay? What you're measuring here is a reflection of what's going on out here, and it takes time for it to come back. And in the context of this discussion, we're talking about phase. So there's, if this were not a pulse, but a frequency signal, we're talking some number of degrees from here to here, some phase angle, plus the same amount of angle or same phase duration coming back. Okay. Let's, what's our next topic? Okay, at the risk of repeating this, but I have it down in my notes that this is part of the earlier video that I lost due to no audio. I'm going to graphically represent what I just said about all the forward and reflected waves. So here we go. I have a forward waveform of voltage. Okay? And just voltage now. My termination is super, right? What's going to happen is I start to shift my load. I go from 50 ohms, a matched condition, to 60 ohms, just a little bit off, 60 ohms. So now I have a little bit of reflected signal. and that reflected signal will come back reflected. So my composite signal rises. My voltage is going to start to increase. As my load continues to increase, now I go to, say, 75 ohms. And 100 ohms. Okay? So what's going on with the current? The current, at the same time, if I draw my current, here's my forward current. It's 20 to 1, so I'm going to draw it. Okay, so current is black. Voltage is red. So if I have a reflected current, it's going to come back 180 degrees. I'm sorry. It's going to come back in phase. My current's going to be reduced. I'm going up. My mismatch is on the high side. So there's my ratio. So my net voltage will increase. So if I drew this again, my net voltage might increase, and my net current will decrease. So when I put my meter across here at 180 degrees, this voltage will give me a high reading, and when I flip it, I'll show a mismatch. In other words, these two will not cancel out, and the higher voltage reading will give me a higher reflected reading. So it's basically how it works. And the same condition holds true if there's a phase shift due to either line length or a reactive load. There'll be a phase shift, and that'll all be reflected in the resultant composite waveform. The way you can tell the differences here is if you have a power meter, it will read erroneously. So the power will not match voltages and currents, or at least not for a 50 ohm system. But that gets back to the position of the meter in the line thing. So I think that's covered everything I needed to cover. The next segment we'll talk about matching, some more, and really get into antenna theory and matching networks, matching impedances and reactances. We're really gonna get into stuff and keep it all relative to phase. See? No math. No numbers. Okay. I think I've covered everything I want to cover for now on transmission lines. We'll do a little bit more when we get into antennas on the next segment. With the exception, I'm not going to get into reactance now, or apparent reactance, but we'll certainly cover that with antennas and how that adds to the whole phase gobbledygook. So what I'm going to show you now, just to wrap up this transmission line stuff, is I got some show and tell. I mentioned this is a piece of line which is cut as a 54 megahertz trap for operation on 28 megs. It's a dead short at this end. It is RG213U. So it is a quarter wave with a dead short on 28 megahertz. The dead short at a quarter wave appears as an open circuit. However, at 54 megahertz or thereabouts, the dead short appears as a dead short because it's a half wave line on 54. And here's what it looks like if you graph it out. I have a little tag here. I made this in November of '92. It's a little while ago. And I measured it on an HP 8920A. I have no idea what that is. I don't remember such a device. I don't own one now. I don't know whether that was a frequency counter or RF voltmeter or spectrum analyzer. It could be anything. But here's the specifications that I measured back then. This would be connected with a simple T connector at the transmitter, or usually at some convenient junction point. But it was just teed into the line. And this is a typical curve. You notice it looks a little bit irregular because there's a lot of other things going on here at all of these other frequencies. You know, it's not a quarter wave, it's not a half wave, it's something else. It's going to be, there's all kinds of phase shifts and things going on at all these different frequencies as you sweep it. But when you put it into a system, it's only going to see specific frequencies. It's going to see whatever you put in it at its fundamental, and it's going to see harmonics. All this other stuff doesn't exist. You really don't have to concern yourself with it. So at 28 megahertz, it's going to appear as an open circuit, relatively speaking. The only losses will be losses from energy, which is in fact traveling down the line to the short, being reflected back, and then coming back to this point, at which point the standing wave reconstructs and appears as an open. But it's still traveling through this line. So there's a little bit of loss, there's a little bit of load at 28 megahertz on this line, strictly due to its losses. If this were a different construction, a much lower loss line, it would have a, appropriately low loss. So I don't know what that loss is. I don't know why it's not on the tag. You'd think I would have measured such a thing, right? But I'm going to just guess that it's about 0.2 dB. There might be about 0.2 dB loss. It's got a little bit of effect on the line, but not much. And a lot of that may even be in the T connector. So, but if we go up in frequency, when we start getting into the 52 megahertz band, there are some notable points that we want to measure. And very often, when you see specifications for filters, now here's where we get into the whole snake oil thing. You gotta look at specifications very carefully when they use words like bandwidth, wide bandwidth. Well, how flat is it? I mean, if you could have a wide bandwidth where they could find some point out here where it's 3 dB down, and some point on the other side where it's 3 dB down, you say, wow, look at that bandwidth. But if you go just a couple of 100 kilohertz or something, inside of that, all of a sudden you've got a hole that's 20 dB down. Then it comes right back up, and now it's minus 6 dB, and then you got another hole, and you don't know what that curve looks like. If you don't see curves, just putting on a package that wide bandwidth, minus 3 dB at this from here to here, and anyway. So anyway, this curve has a couple things going on, and in terms of an attenuator, the 3 dB bandwidth really isn't relevant. I mean, 3 dB bandwidth is relevant where you're talking about a pass filter. Anything that has losses greater than 3 dB, well, it's not passing terribly well. So there, the 3 dB is important. But for something like this, what you're really looking at is orders of magnitude, 10, 20, 30 dB down. So in fact, this does measure the bandwidth at minus 10 is about 5 megahertz. So that's pretty good attenuation, 10 dB down. That means that the signal level from 52 to 57 has been attenuated 10 times. 1/10. 10 dB works out to be 1/10. 20 dB. Now we're down to 100th. We've attenuated from 54 to 55. Everything in that segment of the band has been attenuated 100 times. 20 dB down. When you get to 54.9 megahertz, which, well, you know, it says 10 meters, doesn't it? Let's say 10 or 11. You get to 54.9 megahertz, we're down 30 dB. 1,000 times. So 1/1000th of the signal that was present without this cable is now being attenuated and is dead short. And the fundamental is being allowed to pass. So, yes, is this like, you know, is this like Naughter microwave quality stuff? No. You know, it's amateur radio, dude. But will it solve problems in the shack? Or sometimes stuff like this can just be used as test equipment. You know, make up something like this quickly just to see if it solves a problem, you know, to help identify a problem. Okay, so there's one. Here's another one. This is a variable line. And you see it's pretty short. And it is, I suspect it's a half wave. What does it say? It says 2-meter adjustable stub. No specifications on here. This is probably when I was getting closer to the I don't care mode. Now, for 2 meters, we want something that's obviously lower loss. So this is made out of 9913, which was the quite the hot stuff back in its day. This is made by Belden, and it's a piece of cable. Let me get up close here. And on the end of this cable, see, and towards the end of this cable, I have soldered a brass tubing. Let me get right behind it so it focuses better. I've soldered some brass tubing. What if I do this? Is that better? No, that's not going to focus either. Okay. So there's the brass tubing, which has been soldered through, and the tubing ends here, and I have a piece that slides. So this piece of tubing I can slide in and out. And if I slide it all the way out, you'll see it has some little, don't like the way this is working. I have some little fingers in the end. There's little fingers in here to grab the center conductor. Can you see a little center conductor in there? Hold it this way. I don't know if you can see that. There you go. See that little tube in there? That's the center conductor, which has been soldered on back down here. So when I put this together, I got some slots cut in the end of this too to grab this. So when I put this together and figure out how to make it work, there we go. I have a little red line here to indicate don't pull it out farther than that. So now I can slide this line in to adjust the length of the line, and I can tune it. And this has been cut as a half wave on 2 meters. So therefore, a dead short, again, same deal we've got with this 28 meg line. This is an open circuit on 144 or thereabouts. I can tune it, I can play with it. and anywhere else it's going to exhibit significant attenuation. So this would also, not only with this not only would this work at well 288 megahertz, but it would work well at 440. And that may very well be why I made this. I honestly don't know why I made this. What I was trying to, I think I know it. I think I know what I was trying to take out. I think I had some image issues with a transverter. I think that's what I was using this for. I don't know. It's a long time ago. All right, so there you go. There's a little, not quite a slotted line, but pretty cool. And lastly, I have a duplexer. This is a Phelps Dodge, says right on the label, Phelps Dodge cavity resonator, 144 to 174 megahertz. So what this is, when you hear people on talking about repeaters and they're going up to tune the duplexers, or tune the cans, as they say, this is a key component of a duplexer. Now, this is not part of a duplexer. This is just a notch can. It's a filter, and it's doing pretty much the same thing, sort of in reverse, that those filters do. This is on the input side here. You see these two yellow caps. Let me bring this up a little bit. On the input side, you see these two yellow caps. So that's a in and out. In this case, they can go either way, in or out, out, in. And there's a rod here, an adjustable rod with a nut, and so we can tune this. These inputs actually are connected to a very small coupling loop, and the coupling loop couples energy into a large rod in the middle of this can. It's about 5 inches in diameter. The center conductor connected to this rod, this center conductor is about 1 inch diameter. The characteristic impedance of this can, if it were a piece of coax, would probably be about 100 ohms, 70 to 100 ohms. It's really not relevant in this case, as we're not using it in that mode. So these two loops couple energy into that center conductor, or actually through that center conductor to some extent. So energy comes in on one loop, is coupled to the conductor, and it is provided that energy flows in that conductor, that we have a resonant condition where lots of current is able to be coupled into that center conductor. It will then transfer that energy over to the other loop, and we will have a very narrow, very effective band pass function, and it will attenuate everything else, because at any other frequency this will not be tuned to resonance, and it will not have significant current flowing in the center conductor. At this end, at the other end, it's open. The center conductor traveling from, this is grounded at this end, and then it comes down, and then at some point it just stops, and it's open. So this, at a quarter wavelength, this would present a short circuit to frequencies outside the passband, and that's how that works. So and that's just a cavity. So it's a section of transmission line, actually, is what it is. Now, in repeater operation, and there's a couple of, I guess, patented ways by which different repeater manufacturers do this. But in a repeater operation, they would couple across the input and output with a reactive element, say like a capacitor, a tunable capacitor, or a tunable inductor, or Phelps diet actually had an interesting thing that looked like a gamma match. It was an inductive loop. It's really quite interesting how it works. But the thing is, they would place a reactance across this tank. So we have our can, and we have an adjustable stub here, which is adjustable via a threaded screw. That, you know, we can turn the screw for an adjustment to vary the length, and they would have up on top we would have an input connector and an output connector with a shorting bar across them, and coming off of this would be just a simple loop to basically a tunable capacitor. The tunable capacitor was actually a tube. It was a threaded rod in a tube, much kind of a lot like this, except it was threaded. So you would screw it in and screw it out, and it would change the capacitance here because these two tubes were insulated from each other. So that formed a capacitor. So you would tune this link, and this link would be adjacent to this big center conductor here inside the can. Okay, so I'll just draw that like that. So energy would couple from the link, would couple to this center conductor. But this element, having this element in there, would cause this to pass frequencies above or below. So if you had very little capacitance, this would appear inductive, and it would pass frequencies on the low side of the notch. And if you had a lot of capacitance in here, or is that the other way around? No, if you had a lot of capacitance, it would pass frequencies on the high side, and if you tuned this to be inductive, it would pass frequencies on the low side, I think. But you get the idea. So what you'd get would be, it's time to clean this board again. What you would get is normally you'd have a characteristic where you'd have a big notch in the can. But by placing this element, we'll put it on the high side, by placing an element which is largely capacitive, you would get a very low loss pass frequency, maybe minus 0.1 dB, a nice low loss pass. So this would be your in your receive side of your repeater system. This would be your receive frequency, and this would be your transmit frequency, and you would have several of them in series. You typically 3. You'd have 3 for transmit and 3 for receive. So if you stacked up 3 cavities with this kind of response, you would end up with a total attenuation of I'd say anywhere from 80 to 120 dB, minus 80 to 120 dB attenuation in the stop band, and maybe minus 0.4, 0.5 dB in the pass band, which is pretty good. And then you would do the exact opposite on the transmit side. So on the transmit side, you would pass the transmit frequency onto the antenna, but you would block the receive frequency from getting into the transmitter. You'd also block a lot of other stuff from getting into the transmitter, causing mixing products and noise and trash and stuff you don't want. So no black magic here, folks. It's a piece of coax, and we're using the phase relationships of the RF traveling down a line and being reflected back to do all this cool stuff. It's not really terribly complicated. It's pretty simple, actually. The implementation can get pretty tricky. Some of the engineering, like I said, the link that Phelps Dodge made I thought was pretty cool. It was a little hard to tune because once you broke the lock nut on the rod, it was no longer well grounded, and so the frequency would jump all around like a, you know, spastic Quaker. I mean, it was terrible. You know, then you have to lock the nut and see, well, is that where I want to be? The pass element, by the way, the pass element shifts this frequency way down, or way up, as the case may be. So if you took away the pass element, this notch would move quite a bit. So you're detuning the can by adding this pass element. You're detuning the can, but you're creating a series resonant circuit in one frequency and a parallel resonant in another. And there you go. So it's pretty cool stuff. All right, so that's all I got to show you. I'm going to say we're done for transmission lines. For now, I will cover there will be some more transmission lines in the next segment when we start talking about antennas and how they present themselves to what's in the transmission line, and ultimately how they radiate their energy into the real world and get a signal out, and how to match those antennas, how to get the power into them that we want, how to get bandwidth out of them or not, a variety of things. I hope you'll tune in for that. Hope this wasn't too painful, and my real hope is that some of you now have a more comfortable understanding of how transmission lines really work, as opposed to some of the mythology that I've heard. So there you go. Thank you very much.